Hi, good morning. So the nice thing that I can talk about today, or just say right now, is I'm probably at least the fourth person to say good morning to you. So I hope you're having a really good morning. As you heard, my name is Prashant Rao. I'll be talking about what's new in MATLAB and Simulink. Now, we have over hundreds, a couple of hundreds of things that are new in terms of features and capabilities. And in the next 30 minutes, I'll be able to provide you only a glimpse of these. In the past, I saw a number of you are new to MATLAB EXPO, but for those of you who have been here before, we focused on what's new from our end in terms of how we are helping you increase, or what's new in terms of application depth, application breadth, workflow depth, and platform productivity. And we changed this around a bit. So today, I'll be trying to talk to you about what's new from your perspective. And let's take a look at how that works. So in the keynote, you heard about a number of different application areas, for example, for AI, from quality control, autonomous vehicles, or also medical sciences. And if we think about this further, this is part of a broader trend, the trend of software in everything or algorithms in everything. That means algorithms are being put into places where they were not before. For example, in manufacturing, process automation in manufacturing, or also intelligent systems for farming and agriculture. In risk analytics, for example, for financial applications, and of course, in autonomous systems like this humanoid robot called Justin. Now, Mike in his keynote highlighted the need for workflows that span across the entire development process. And in order to be able to so that you can be effective in implementing your algorithms in whatever platform you require. So I'll be talking to you on this theme of how MATLAB and Simulink is an ideal environment that spans the overall workflow, and what's new in MATLAB and Simulink that helps you do your job better. One of our driving strategies is really around simplifying, helping you simplify your work and enabling you to work at higher levels of abstraction. This approach helps you focus more at your task and not at the tools that are required for you to do your task. So the goal of this session is really to show you what we have new in this. As I mentioned, it'll just be a glimpse. I'll be taking an example of a simplified workflow to take you through this. So this simplified workflow exemplifies how you can use MATLAB and Simulink for your design. It starts with inputs, moves over to a design phase, and then finally provides you, surprise, outputs. So taking this workflow, let's take a look at it in the context of AI. As we started off on the AI theme. So to ensure that we're all on the same page, I know Dr. Jammu provided one definition of AI, and I will provide a similar but a slightly different definition of the AI, just to provide more clarity about what AI is. So the capability, AI is the capability of a machine to match or exceed intelligent human behavior by training a machine to learn that desired behavior. So let's focus on this part, training a machine to learn that desired behavior. And for those of you who were here last year, you would remember some of these slides or this concept, that there are two ways to get a computer to do what you want. For those of you who are new, I'll be going over this a bit. There's a traditional programming approach where we provide our computer with data and a program, and the computer provides us outputs. And using a technique called machine learning, this is flipped around. So we provide the data and the expected output, and the machine provides us the program. Now, it's not quite fair to call that a program. We'll call it a model in the context of machine learning world. Now, when we take a look at this overall, let's say for machine learning, or for AI, there are two primary techniques that are used to implement AI, machine learning and deep learning. These techniques are based or require a large amount of data, oftentimes labeled data. That data is taken, in the processing or in the design phase, in the processing phase, that data is processed to train the model, so the machine learns, and then the model that is then created is then used on unlabeled data sets to actually provide you the predictions that you require. Now, this maps very well into the workflow that I just described of inputs, design, and outputs. And let's take a look at this in the context of deep learning applications. And let's start with what's new in MATLAB and Simulink for deep learning in the data phase. So for the inputs. Image and video applications are very popular usages of AI or for deep learning. And these, as mentioned, require large number of data sets that are actually labeled. The labeling process is time-consuming, repetitive, and, for lack of a better word, quite boring. So using apps like the image labeler app over here, you can actually semi-automate this process. So the app will automatically detect and label objects in the scene, and you can add on or identify objects yourself and label them yourself as well. Now, pixel labeling can also be used. This gives you a higher level of precision, and you can interactively define the boundaries of an object in the scene, and use this, for example, to develop a semantic, or use semantic segmentation algorithms, which then give you a deeper insight or deeper information into the image that you have, more than, let's say, object detection and classification do. Now, taking this from images to other data sets, there are similar kind of apps that are available for you for signal data, as well as for audio data. So you've got some data now. Let's move to the next phase, the design phase, where we'll actually develop the network that we require. In this, we also have an app. It's a deep network designer app that helps you create the network without the necessity of you coding it up. You can just drag and drop individual layers of your network into the canvas, connect them up, and if you have existing networks, you can import them into the app as well, and you can edit those as well. The nice thing about this is that you can do this without writing any code, so you can concentrate on visualizing and actually building the network that you require. As the next phase, you can analyze the network for errors, and then export it to your workspace so that you can actually train your network. Another way of getting started quickly, for example, for deep learning, is to use transfer learning. So use existing pre-trained networks. With a few lines of code, you can import these into MATLAB and then use them for your application. You can also adapt them for your specific needs. We support a number of these existing networks, and the support for these is increasing with every release. To give you more flexibility, you can also import models from other frameworks, for using model importers, for example, for Keras TensorFlow or for Caffe. And using the Onyx industry standard framework, you can import and export or share your models from MATLAB to even further frameworks. So this allows you to interface with many, many other frameworks for deep learning, for building your deep learning applications. So now you have the data, you have your network. What are you going to do with it? We provide code generation capabilities so that you can generate code for your deep learning model and target NVIDIA GPUs, for example, with CUDA code, or ARM or Intel CPUs using C code. Now, this is not just the deep learning part of your application, but pre-processing and post-processing steps as well. So you can harness the power of a GPU or also of the CPUs over here for your entire application. So that was this workflow in the context of deep learning, let's take a look at another application, a slightly different one, reinforcement learning, which is a machine learning technique based on trial and error methods. So taking a look at reinforcement learning, essentially, this can be used for controlling highly dynamic systems. For example, aircraft, the robot in the middle, or autonomous systems. And the concept works by running multiple simulations or trials on the system and rewarding good behavior. It's kind of like watching how a child learns to walk over here, in this case. The child falls down. Well, that's not really a reward, but you do reward when the child can walk all the way to you. Now, you can imagine that doing something like this with actual physical prototypes can be very, very expensive and sometimes even dangerous. So we can use simulation to actually develop our reinforcement learning applications. And in this case, we may not have data from existing systems, so we can generate the data using scenario design as well as simulation-based data generation techniques over here. And Simulink is a great platform that enables you to run simulations, thousands and thousands of simulations, and generate the data that you require to actually build your reinforcement learning application. We have a reinforcement learning toolbox that is released in Release 2019A, which you can use for this. And the end result of this could be something like this robot actually following the line. If you want to know more about this, we have a talk later today, Deep Learning and Reinforcement Learning Workflows in AI in the Deep Learning and Autonomous Systems track. So that's AI. Now, if you're not working specifically in AI, there's plenty of new things in MATLAB and Simulink as well. And I'll take you through this workflow and giving you insight into what's new across the different parts of this workflow. So we start with inputs. Inputs could be your idea. It could be requirements. It could be data, for example. We move to the design phase where you're analyzing the data, creating your model, building your application. And then we move to the actual outputs phase, where again, this could be the output of your work, it could be the answer to the question that you asked, the result of your research, or also an application that can be integrated into further applications or code that is running on a specific targeted device. So let's take the first step of this workflow, the input stage. Now, data is actually driving this whole trend of algorithms and everything. And we can get data in various different forms. For example, these are operator logs from a truck fleet operator. As you can see, this data is mixed, and it has text as well. So let's first think about the text. So we need to bring the text into MATLAB, separate the text out, and represent it in some way. And that's where data strings, string arrays, come into play. In addition, we have got a couple of functionalities or capabilities that enable you to visualize or classify the text that you've got. And you can use both machine learning and deep learning techniques to actually operate on the text data that you've got. There is a capability for other languages as well, not just English. And so that's basically from the text side. Now, what if you don't have data? You may need to create your own data. In Simulink, we have the signal builder block with which you can create data. But you also now have the signal editor app over here with which you can interactively or visually create your data as well. So this makes the process of creating your data easier. And you can feed this into your simulation, for example. Sometimes, or specifically in predictive maintenance types of applications, you're acquiring data from sensors from a certain machine. And then you're training your model, which will then actually predict failures of your machine or of other machines. Let's use this as a scenario, as an example, as we move to the next phase of design. So when we acquire the data, we need to do multiple steps to actually process the data and build a machine learning model. This is a workflow that describes many of these steps. And in this, there are challenges that you will face specifically to understand or identify the useful data for your application. Which data is actually going to be relevant in predicting the failure of your machine. Several techniques can be used for this, specifically to extract the features from the data and select these. And I'll showcase a couple of examples over here. This is a diagnostic feature designer app, which allows you to visualize the data that you're receiving that you've got. And you can also then extract features from this data. There are hundreds of possible different features that you can extract, and the app allows you access to time domain as well as frequency domain feature extraction techniques. Once you have the features extracted, you can rank them using one-way ANOVA, for example, over here, and then use this set of features to actually train your algorithm. You can export this set of features directly from this app to something that we call the classification learner app, which can be used to identify the right classification model that can be used for developing a machine learning algorithm. So interactive apps like this are really helpful and are a good example of working at a higher level of abstraction. Another example of working at a higher level of abstraction is provided with Stateflow, which enables you to graphically model, design, simulate, debug, and execute state machines. Until the last release, Stateflow was available for Simulink users, but now in 2019A, you also have access to Stateflow in MATLAB. Now here's a brief example of how powerful this can be. Take this little example of a switch. Now the switch in Stateflow or the switch in MATLAB are very similar or are probably equally easy to develop. But when you add in further real life or real world effects, like let's say hysteresis or debouncing, your code can expand quite a bit, whereas the state machine in Stateflow, or the representation in Stateflow, is very graphical and gives you exactly what you require for this. So another example of using Stateflow is here, where Stateflow is used to control a UI. Here in this case, you can graphically see the state transitions and the state of the UI. We have timer capabilities, temporal capabilities that enable you to build things like timers. This enables you to build applications, for example, for data acquisition, event-driven models, or also, like in this case, UI control, much easier, and you can concentrate on your application rather than the actual code. Simulink is a great platform that enables you to work at a higher level of abstraction. And we're continuously trying to make the usage of Simulink easier for you. Essentially, help you focus on the model or the algorithm that you have, and not so much on the functionality of editing and creating that model. So as one of us developers put it, enabling you to edit at the speed of thought. And there's several smart editing enhancements within Simulink. And I'll show you a couple of these. One of them is, for example, the automatic port creation, with which you can actually drag and drop a signal line from the boundary of a subsystem to the boundary of another subsystem, and automatically create support for you without having you to drill into the subsystem and include or bring in a port block. Now, editing parameters of blocks has become easier as well. You don't have to open the dialog box. You can edit these directly in the canvas itself. Sometimes when your models are large, you have large number of parameters. And we can provide you suggestions for the parameters that you can use. These suggestions are basically taken from the model workspace and the data dictionaries that the models have access to. Oftentimes, your model can be quite complex. Hierarchies can be very deep. And now in 2019A, we allow you to open up a model reference within the same window itself. And you can see this at the top with the breadcrumbs. If you still want to open the model, a model reference in another window, you can do so with this icon on the bottom left. And this is the feature I think I love the best. It's actually the predictive quick insert. So with predictive quick insert, you get a set of suggestions for the next block that you would want to insert into your model. In a case like this, where we're using Simscape blocks, you will be provided only with suggestions of blocks from that domain or that can be connected to that domain. The nice thing about this is that this learns as you go along. So the more you use this capability, the more predictive quick insert gets better and better and gives you the right suggestions. You can even train it with a library of models that you already have and train it so that you can use it right straight out of the box. In some cases, you may want to control the execution of model components. Now, before 2017A, you had to create an export function model. After 2017B. After 2017B, we introduced schedulable rate-based models, which can be controlled through a scheduler, for example, that's built in Stateflow. In 2019A, we have the schedule editor that allows you to graphically partition and set up the dependencies between different components in your model. Not only can you visualize this, but you can actually change the scheduling order of your model as well in this manner. And you'll see that it actually arranges the blocks very well at the end. So those were some things that are new in the design phase. Now let's move to the output phase. Oftentimes when we want to generate C code, we want to embed that C code into another environment. Sometimes the code that you generate is column major, but the environment that you want to integrate it into is row major. And now in 2019A, with a few mouse clicks, you can actually generate code from MATLAB or from Simulink that is then row major or column major, whichever way you'd like to go. I think for those of you who are targeting embedded devices, this will be a welcome addition to Simulink. When you want to visualize the code, if you wanted to do it in the past, you had to go back and forth between the model and the generated code. This can be quite tedious at times. And now with the new code view capability within Simulink, you can view the model and the code side by side. So you just open up the code perspective, and you can trace from the model blocks to the code, and vice versa, from the code back to the model as well. Now, these were some capabilities that are new on the output or generation of code from Simulink. Let's move over to MATLAB. In MATLAB, you can share your work as well. Live scripts enable you to build, to include text, data, code, hyperlinks, etc., within your actual environment. And you can share this now in the form of a static document like Word. So we can generate a Word file directly from a live script. And you can also share the live script as is with others. And we now have capabilities like some UI elements as well, like edit fields, sliders, and so on. This enables people who you're sharing your live script with to actually just change a couple of parameters, and they can even hide the code in in these cases, so that they can concentrate on the parameters or seeing the effects of changing the parameters directly. Apps can be built. The app designer is a great environment that helps you build apps, and you can share these, you can package these and share these with others. You can share these with people who have MATLAB, or also deploy these onto PCs where no MATLAB is available. And if you want to really make it easy for people you're sharing it with, you can provide an app in the form of a URL just by deploying it as a web app, for example. So these were some new capabilities. I gave you a glimpse of what's new in these 3 phases. There is a further phase, and that is the architectural design phase. Oftentimes, you want to define your architecture early on, but the definition of your architecture also has implication on the implementation of your system. So we now have capabilities to help you define the architecture that bridges essentially the gap between requirements and the actual model. The System Composer product is one such capability with which you can define your software architecture and also define the interfaces between the different components of your software. You can link it directly to Simulink, so you can use Simulink to build a bottoms-up design and then link it back into the System Composer environment. We have a session on this today. We also have a demo booth outside on systems engineering, requirements to architecture, to simulation. Going past the design of software, we also have new capabilities using the SoC block set, so system on chip block set, to define and develop your SoC hardware and software architecture, and a new product called AUTOSAR block set that enables you to define your AUTOSAR architecture as well. Now, as mentioned, these were 4 steps that enable you to build algorithms in everything. There are some more steps that span all these 4 phases. And those are the steps of test and verification, collaboration, and scaling. So let's take a look at what we've got on the test and verification side. Now, engineers and scientists are increasingly using best practices that software developers already have had for a number of years. And these are being adopted more and more for developing engineering systems. One such, and many of you may be already aware of this or be using this already, is Agile. Now, the Agile workflow depends on collaboration and running several iterations. And this workflow supports an Agile workflow really well. So when we look at it, we can run iterations and use these models to collaborate with in a very, very nice manner. Now, let's take a look at test and verification further. To bridge the gap between requirements and the model, we can import requirements from third-party tools into models using the RecIF interface. And now in 2019A, we can edit these requirements in Simulink and export them back into the requirements tool that you're using as well. This enables you to ensure that you are covering all your requirements in your model as well. Simulink Design Verifier can be used also to verify and validate your model against requirements. And now Simulink Design Verifier also supports the generation of test vectors when you have included C, your custom C or C++ code in your individual designs, so in Simulink and Stateflow itself. You can find out more about this in a session later today as well in the Systems Modeling, Implementation, and Verification track. So MATLAB can also be used as a unit test framework. There are several capabilities around this. There are functions that enable you to build verification algorithms within MATLAB itself. There are capabilities that enable you to run tests automatically, and capabilities to enable you to visualize results of these tests in a standard format. One such application of the testing framework is to test apps. And here, you can programmatically define gestures that will actually run or change UIs. So you can use this to automatically test your UI framework. So the app testing framework is available. There's also a performance testing framework that enables you to run performance analysis on your MATLAB code, and you can also trace or track how your MATLAB code has been performing over time to ensure that changes in your MATLAB in your code are not degrading your performance. Continuous integration is a key backbone behind agile workflows. And we have a plugin for the popular Jenkins continuous integration server that's available directly on the Jenkins website. And you can use, so now as projects become larger, you can use projects within MATLAB, just like you can use projects in Simulink, to actually package up all your work or all the files that you require in your project and run things like SVN or analyze dependencies and track and control changes as well. Now, when it comes to scaling up, running simulations iteratively, in 2017A, we introduced the parsim command. After that, we introduced the simulation manager that enables you to visualize the results of your simulations. And in 2018B, we've introduced a batch sim command, which enables you to offload your simulation so that they can run completely on a cluster. This is all part of what's available also with MATLAB Parallel Server, which enables you to take computations and scale them up onto a cluster or onto cloud. If your environment also has GPUs, you can use the power of a GPU as well. MATLAB Parallel Server was earlier known as MATLAB Distributed Computing Server. So that was a quick glimpse of a number of things that's available across the different workflows, across MATLAB and Simulink, and across the different phases of the workflow. As highlighted in the keynote, it's important that your work, that tools span the entire workflow for you. And this is where specialized workflows are important, especially specialized tools that enable you to do the work that you require for your application area. And we have new capabilities that enable you to do this for communication system design with the 5G toolbox, modeling physical interconnects, high-speed physical interconnects with the SerDes toolbox, and developing analog and mixed signal designs using the analog mixed signal block set. Now, having brought all those pieces together, let's look at one application area where the workflow comes together. The application area we're taking is autonomous systems, where you typically have 3 different phases to develop your autonomous system: perception, planning, and actual control or actuation of your autonomous system. And let's see what's new in the perception part. So this is an example of acquiring LiDAR data and segmenting it and clustering it to identify vehicles. The data can also be used to identify the driving path or the ground plane. And 3D bounding boxes are available to actually track the different vehicles. These are new capabilities that are available in the sensor fusion and tracking toolbox. The automated driving toolbox enables you to build a cross map of your vehicle with which you can run actual path planning algorithms. So you can actually simulate or run the simulation for a valet parking, automated valet parking algorithm over here. And this is still a simulation, but maybe in a couple of years, this becomes reality, and we can have our vehicles parked automatically in this hotel when we come for the next MATLAB EXPO, maybe MATLAB EXPO 2025. I don't know. Staying with the theme of automated driving, you can now run the complete simulation of a driving scenario. For example, here, lane keeping and distance spacing. Data is generated from MATLAB and Simulink. Camera and radar data is generated from Simulink and is used by the model predictive control toolbox to actually ensure that the vehicle stays in track and is following the lanes. There are several new capabilities on this front as well, enabling you to process and track LiDAR data with the computer vision toolbox, the ability to import maps and roads in the automated driving toolbox, and several capabilities around guidance and navigation for UAVs in the robotic system toolbox. There is more information on this today at demo booths outside, as well as at this talk, automated driving system design and simulation. So that said, that spans the various different capabilities. So within our world, so the world of engineering and science, MATLAB and Simulink are ideal tools that enable you to work, to concentrate on the work that you require to do and get you to your goals. We've added a number of capabilities already, and we're happy to hear from you about more things that you may think we require. This presentation just covered the highlights, and this was just a glimpse. There is more out there today. Just as a key takeaway, one thing that you can do to get started if you're new to any of these technologies is look for the on-ramps. We have a MATLAB on-ramp, a Simulink on-ramp, and a deep learning on-ramp. These on-ramps are free, they're online, they're interactive, approximately 2-hour tutorials that you can run through and with which you can learn the basics of MATLAB and Simulink. Of course, we are available to also help you get started in any way possible with all the engineers that we have today. Thank you very much for listening to me.